me see. Okay, so we are happy to have Tudor Padurariu from Columbia, and the title is on the screen, Relative Stable Pairs and a non-Calabi-Yau wall crossing. Please, Tudor.
Yes, yeah, thank you for the invitation to speak in the seminar. Okay, so first I should start by explaining two of the terms that appear in the title. So the first one will be relative stable pairs. So this will be part of data that is called an enumerative theory. So this enumerative theories in the stock will be associated to smooth, projective threefolds over the complex numbers. So mentioned that it is something that defines an enumerative theory. So in this talk, the enumerative theories will be defined using sheaves. More precisely, using complexes of coherent sheaves on X. Okay, and let's see. So the idea behind them is that we would like to study curves, say smooth curves. We would like to count, so we would like to study the moduli of such curves, and then using some incidence conditions on X to count the number of such curves with some given incidence conditions. And in an enumerative theory, we want to compactify the space of such curves. And when using coherent sheaves, actually what we'll remember out of this data is the ideal sheaf. So we would like a moduli of sheaves that contains all these ideal sheaves. And the moduli of these objects that I'll define later in the talk, called relative stable pairs, will be such an example. And then
when you say moduli of shifts on what? On C or on X or on moduli?
So this will be moduli of coherent sheaves on X.
On X, okay.
Yes. That contain all these ideal sheaves IC for C.
And FC is on C, right? Or is that a sheaf on X defining the
IC is a sheaf in X. So this is the ideal sheaf in X.
Okay, thank you.
So this is yes. And in an enumerative theory, what will happen is that we will have a certain algebraic cycle called the virtual class of a given expected dimension. So I'll say a few more words about these constructions when I discuss examples. And we will study the intersection theory, so intersections of this virtual class with insertion classes, so classes from X, coming from X. I'll define this more precise when I talk about particular examples of enumerative theories. So this will correspond to counts of curves on X with given incidence conditions. Okay, so this is what is an enumerative theory. So the plan will be to discuss three such examples in this talk. So the first one is defined using ideal sheaves. The second one is defined using stable pairs. And the last one will be the one mentioned in the title, using relative stable pairs. Okay, and before starting to talk about ideal sheaves, there is another notion in the title, that of wall crossing. So for the purposes of this talk, wall crossing will mean a relation between two such theories. So this can be also interpreted as a unusual wall crossing of given a stability with, induced by a given stability condition. We'll not use that language. So when I'll discuss this comparison between stable pairs and ideal sheaves, I'll make clear what I mean by wall crossing. Okay, so the first case is that of ideal sheaves. So this is also called Donaldson-Thomas theory. So let beta be a homology class on X, and let n be an integer. And we look at the following moduli space. So this is the moduli of ideal sheaves, IZ, where Z inside X is a subscheme with support beta, and with Euler characteristic of a structure sheaf N. So we want to compactify, well, not necessarily compactify, but we want to find a proper space that contains all these ideal sheaves IC for curves, and we allow, we also, we add in this moduli space the ideal sheaves, not only for smooth curves, but for all subschemes with the same support as C and with the same Euler characteristic. Okay, so this is the same as the Hilbert scheme of curves on X. But it is more convenient to work with ideal sheaves than with structure sheaves of the curves, as I'll explain in a second. Okay, so let's see what is the deformation theory of this space. Okay. So the infinitesimal deformations will be given by x1 on X of IZ, IZ, and the obstructions, deforming this to higher order, will lie in X2, IZ, IZ. And it is actually convenient to only look at deformations for fixed determinants, for trivial determinant. And then we'll add a 0 here, meaning this will be the kernel from the X spaces to the ith cohomology of the structure sheaf on X. So this will be the trace-free parts of the X groups. And actually, the trace-free parts of X0 and X3 will be trivial. And this is where it is important that we use ideal sheaf and not structure sheaves. And let's compute the expected dimension. So the expected dimension will be the difference between the dimension of X1 and the dimension of, the dimension of X2. So I was saying that the trace-free parts of X0 and X3 vanish. So we can use Riemann-Roch, and this will be the intersection between beta and C1X. Okay, so now the observation is that in general, X does not have this expected dimension. So you can actually have multiple components, multiple irreducible components, and some of those irreducible components can have bad singularities, so not necessarily LCI, which X will be far from smooth, and also some of those irreducible components will have dimension larger than this expected dimension. However, what happens is that there is an algebraic cycle on X that can play the role of this of its fundamental class, and which would coincide with the fundamental class if X had LCI singularities. There is LCI singularities, and it would be of the expected dimension. There is a virtual fundamental class. Of expected dimension on X.
So I'm confused with X and M. X has expected dimension 3, if I understand correctly. It's a threefold. So do you mean a moduli space or what? Because I am confused with the letters. Maybe I'm stupid. Your X is a threefold, if I am not mistaken. Yeah.
Yes.
Beta is a class of a curve, roughly speaking, maybe virtual curve. So on your previous in your previous notation, you spoke about M virtual, not X virtual. There is
yes,
so typo on the next page. I think it's not X virtual but M virtual. Yeah. However, there is.
Yeah. Sorry. Yeah. Sorry. Thanks.
Okay.
Oh yeah. I was sorry. Yeah, I meant the moduli space. So I n x beta. So this space, of course, X is smooth. It's a smooth threefold. So I'm saying that the Hilbert scheme of curves does not have the expected dimension, but that there is a virtual class of expected dimension. So there is an algebraic cycle of expected dimension. Yeah, thanks. Yeah, sorry. So once again, X is smooth. So I was saying that even for X, a smooth threefold, this Hilbert scheme of curves, or if you want this moduli of ideal sheaves, can have bad singularities. It will not have the expected dimension. It will have irreducible components of dimension larger than that. Nevertheless, there will be a class that will play for us the role of the fundamental class. And this class will be in the expected dimension.
And the E dimension is defined in this way. It's because X is a threefold, or because of the Z has a cohomology class beta second.
Yes.
In general, I could expect to have higher X to I's, not just X to 1, X to 2.
Yes, yeah. In this case, it also has X3, but the trace-free part of X3 is 0.
Okay, thanks.
Yeah. Yeah, so it's important that we work on a threefold for this theories using coherent sheaves. So now I'll define some integers. So this will be the so-called Donaldson-Thomas invariants. So this will be the numbers. So then we'll put this in generating series, and the generating series will be the quantities that we compare across enumerative theories. So let first I be the universal ideal sheaf on x times I and x beta. Let gamma be a cohomology class on x, and let k be a non-negative integer. And then we use sort of tautological classes coming from the ideal sheaf, from the universal ideal sheaf, and this class is gamma called insertions to define some operators on the homology of I and x beta. So the operator will be like this. So they depend on this level k. So this will tell me what part of the Chern character of I need to take, this k. And gamma is an insertion, a class that will correspond to an incidence condition on x. So this will go from the homology of I and x beta with q coefficients into the homology of I and x beta, once again with q coefficients. And the formula is as follows. Okay, so I1x. So this is pi 2 lower star Chern 2 plus ki pi 1 upper star gamma intersect with pi 2 upper star. And now given our cohomology classes and with our levels, we define the following integer. So this will be a Donaldson-Thomas invariant. So we will integrate over the virtual fundamental class. CH2 plus K1 gamma 1. CH2 plus KR gamma R. So this notation means the following. So the virtual fundamental class, so this is an algebraic cycle. It will define a class, a homology class in 2 times the expected dimension. And then we apply the rth operator to it. We'll obtain a homology class, and we repeat this r times in order to get an integer. So now we define 2 generating series. All the results will be in terms of generating series. So given gamma, so this notation for gamma, it's a shorthand notation for R classes, and also K is a shorthand notation for R descendant levels. So this generating series will be a Laurent series in Q. The coefficients are this Donaldson-Thomas invariant times Q to the n. And then we also define the full series. After all 2-dimensional homology classes. Okay. So now there is an issue with this theory.
So, Tudor, I have an issue. You denote by Q 2 different parameters. The second Q is a multi-index, yeah, the one which is below, yeah, it's Q1 yes. And okay, yeah, okay.
Ah, okay, yeah. Yeah, I think some people use different notation for the Euler characteristic and for beta.
Yeah, that's what I mean. Okay, okay.
Yes, yeah, yeah. Yeah, so there is an issue, and the issue is that these numbers are a little too large, meaning that in so maybe I'll write on the next page, sort of the DT theory of points. contributes to DT theory for any fixed class beta. Because in the Hilbert scheme, we'll have structure sheaves for subschemes where C is some curve, but then we can also add any subscheme of dimension 0 that we want. So it's actually probably better to study.
Yeah, you did not say what corresponds to beta equal to 0. I mean, you declare that it's Hilbert scheme of curves. So then somehow it sounded like you excluded points, but in fact you don't. Its support has dimension less or equal than 1, so it can be 0.
Yes,
Okay.
yes, yeah. I was not precise then. Indeed, beta can be 0, and then this INX beta will be the Hilbert scheme of points on X. And in this case, the expected dimension, which was beta times C1x, will be 0. So yes, when beta is 0 and we deal with the Hilbert schemes of points, we will not have insertions. We have, for fixed n, just one number, one Donaldson-Thomas invariant. Okay, so I'll say in a second what the DT theory of points is. But so I was saying, yes, that this DT theory of points contributes to DT theory of any class beta. So it seems that it is better to study the ratio DT x beta q gamma k divided by the DT theory of a point. So now, okay, so I'll mention what this DT theory of a point is the product and larger or equal to 1, y minus q to the n minus n. So up to this point, this is McMahon's function. So it is the generating function of three-dimensional partitions of a natural number, n. And we raise it at the power, the Euler characteristic of x. Okay, and now, why is it better to study this? So we get rid of the contribution of points, but then this ratio also appears in the following conjecture.
Sorry to interrupt you. So this the 0 part, beta equals 0, this McMahon function formula, is that only for the threefold, or this can be more general?
This is a good question, but this enumerative theories that I'm looking at can be defined only for threefolds.
Okay.
This procedure that I'm using.
Okay, thank you.
I think there is some recent work for fourfolds of extending it, but I'm like of Renemo. Yeah, I don't know more.
Yeah, but I'm not sure whether you can have this nice answer. I think the computation of four-dimensional Young diagrams, it requires more complicated measure than for 3D. Somehow, I think for 4D, it's more difficult. At least what I heard from physicists. Yeah.
Oh, okay. This ratio also appears in the following conjecture of Maulik, Krasov, Volkunkov, Pandharipande. So I'll just state one part of it. So the main one is that, I'll not be precise about, is that there is a precise relation between Gromov-Witten theory and DT theory, that they are equivalent. So if one knows the other, one can determine the other for threefolds. But on the DT theory side, one considers this ratio. So the DT theory of class beta divided by the T theory of points. And they also conjecture that this is a rational function in Q. Whereas of course, the one where we do not divide by points is not a rational function, because this dtx is not a rational function. So now it would be nice to have a geometric theory, so another enumerative theory whose generating series is precisely this ratio. And this is what stable pairs do. So I'll discuss the second enumerative theory, that of stable pairs. So this is also called Pandharipande-Thomas theory. So now the objects, namely this stable pair, so the objects that are parametrized in our moduli space, are not sheaves, but complexes of sheaves. And they are two-term complexes of sheaves, where one term is the structure sheaf, the other one is F, which is a pure one-dimensional sheaf. So we see that here we rule out the situations where we have a curve and points. We also assume that its support is beta before, and its Euler characteristic is n. And moreover, we assume that the cokernel of S, this section, is zero-dimensional. So these are stable pairs. And so initially we had ideal sheaves, which were surjections from OX onto the structure sheaf of a subscheme. So here we have these other complexes, and they can be also characterized as surjections, but not in the abelian category of coherent sheaves, but in a different abelian category called the tilt. Okay, so I'll denote this is Pnx beta. This is a projective scheme, is the moduli of such stable pairs. And it had been constructed by Le Potier. And this also has a virtual fundamental class of expected dimension. And the expected dimension is the same as the one before. And one can define this generating series. So one can also define PT invariants now with insertions and put those in generating series. Oh, yeah. So one last thing is let's see how this F looks like. So it will be in a short exact sequence. OC. Maybe I'll use this and to not confuse it with the C that I used before. Q, 0. So OD is the image of the section S, and Q is the cokernel of S. So F is pure of dimension 1, so OD will also be pure of dimension 1. So D is a Cohen-Macaulay curve. Q is zero-dimensional, so it's a bunch of points. F is an extension of OD by Q, and because F is pure, this forces Q to lie on D. So the picture is something like this. So now the points are not allowed to wander, but they will be on the curve D only. So it seems plausible that, well, at least these invariants will be smaller than the DT invariant, and it's plausible that they actually provide a geometric interpretation of this ratio that I mentioned. So this is the conjecture of Pandharipande-Thomas.
By the way, in what generality it's proven? Oh, your formula. Okay, sorry. you should formulate.
Yeah, I'll say a few words about it. Yeah, so their conjecture is that this PT series with insertions equals the ratio of the DT series, Donaldson-Thomas invariants. So these were the ones defined using ideal sheaves divided by the DT theory of a point. So this is known for X Calabial threefold. So a Calabial threefold means that omega x is trivial. And not known beyond that. So the reason is that in the Calabial threefold, the proof does not use this definition of DT and PT invariance that I said. So before I say a few words about that proof, so this is so the proof for Calabial threefolds. This was given by Bridgeland, Toda, using the Joyce's motivic algebra.
Yeah, but I remember I spoke to Rahul many years ago. He told me that if you formally apply our wall-crossing formulas just without justifying them, then it will give you the proof of the conjecture. So basically, when you, if you know for some reason that the wall-crossing formula which we establish with Maxim holds and is just automatic. So you don't kind of motivic whole algebra is just a way to package these wall crossing formulas just in one formula. So it's kind of a little bit.
Yeah. So you're saying that this is for the Calabial threefold, right?
Yeah, just for threefold. Yeah, for threefold.
Yes. So this theory indeed packages this, and an important ingredient in all this theory, I think it's a conjecture of yours with Konciewicz, the no-pole conjecture.
Yes. So our motivic whole algebra is a bit more complicated. I mean, it's derived, so then it's kind of it's more difficult to use it. Yeah. I mean, just for people maybe who knows it, basically it sounds scary, but there is just one formula, wall crossing, which roughly shows how the virtual number of semi-stable objects changes when you cross certain real codimensional wall. And if you know that this formula holds, then this conjecture is true. But the difficult part is to show that it holds. Yeah. Okay.
Yes.
Mm-hmm.
So also in my title, I mentioned wall crossing. So this conjecture is an example of a wall crossing. What I mean by wall crossing. So maybe I'll say a few words about this Bridgeland proof. So, or why one can prove this conjecture for Calabial threefolds. And I was saying in this case, there is a completely different description of this DT and PT invariance using this thing called the Variance function. So this is an integer valued function. Let's say I'll do the case of DT theory. And then It's virtual fundamental class. So there are no insertions in the Calabial 3 case because C1x is 0. So then for fixed beta and fixed n, we have only one invariant, the virtual fundamental class. And this can be written as this sum after all integers a, the Euler characteristic of the locus where the Variance function is a. So what is the origin of this Variance function? Well, so in this, once again, it's very important here that we use Calabial locally near P. The spaces are given is the critical locus of a function on a smooth space. And let's see, so and this Variance function at P, it's up to a sign the Euler characteristic. So now, so is the critical locus. So we have a natural sheaf using this description, namely vanishing cycles of F. If we take its stock at P and its Euler characteristic, we get this Variance function. So now this Bridgeland proof, or also part of this motivic algebra, is that because we also have this description using the Variance function, that we can use cut and paste techniques to understand how I n x beta and P n x beta compare. And then we can apply vanishing cycles at the end. And then there are some results that say that vanishing cycles respect well the structure of this cut and paste thing that's understood in this motivic algebra of Joyce.
Yeah, and here it is important that this moduli space is a scheme. In fact, it's kind of, yeah, so smooth scheme, so you can apply this Variance technique.
Yes, yeah. Yes, yeah. And you don't divide by 0 by elements in the logarithmic group. You specialize to 0 when applying Euler characteristic, yes. Okay, so this is the conjecture. And now, let's see, so I'll talk about this relative stable pairs. So these are, let's say, a version of enumerative invariance for singular schemes, for singular threefolds given a resolution. So let's take a map like this. So X might be singular now, so both of them are projective threefolds. And so Y is smooth. But we assume that X has rational singularity. So RF lower star of OY equals OX. And
well, this is a restriction. Yeah, it's kind of like crepant resolution. Is it the model example or what?
Yeah. Yes, yeah, crepant resolution. Yes, yeah. So for example, okay, maybe I'll mention the inspiration for Bryan-Steinberg to define this invariance is indeed the following crepant resolution conjecture. So for certain Calabial threefold orbifolds, for example, Cn mod Z mod n, where the action here is with weights k minus k0. This has a core space. And this core space has a crepant resolution. And there is this equivalence of Bridgeland-King-Reed that says that the derived category of bounded of bounded complexes of coherent sheaves on X is equivalent to dB of Y. Oh, so I should say here, this is a crepant resolution. And this crepant resolution conjecture compares enumerative theories between X and Y. So it says that this dt, the full dt theory of X, Q. Okay, so this there are no insertions, so both curly X and Y are Calabial threefolds, divided by dt X 0 Q equals to the dt theory of Y Q divided by dt Y exceptional. So this is the sum of dt Y beta for beta and exceptional class. So the left-hand side has a description using stable pairs. So this will be pt curly xq. And we would like some enumerative theory that spits out this ratio as well. And this is this Bryan-Steinberg theory that I'll introduce in a second. So this was the inspiration for Bryan-Steinberg of finding an enumerative theory whose invariants are precisely this ratio on the right-hand side of dt invariants, and try and connect the pt and ds invariants in this way, directly. Yeah. Okay. So first I'll mention the definition, and then I say what is known about this invariant. So we want, once again, to parameterize two terms complexes where f will be in a category F and the co-kernel of S will be in a category T. So now who is T? So this will replace torsion sheaves from the stable pair story. So these are sheaves Q, sheaves on Y, such that RF lower star Q is either 0 or it is a zero-dimensional sheaf on X. So in particular, the higher cohomologies will all be 0. And F lower star of Q is either 0 or a zero-dimensional sheaf on X.
So I'm a bit confused. So by your notation, I think that you want to construct a torsion pair, but I would like to understand on what abelian category. Because stable pairs, yeah.
So this is a sheaf.
Okay.
Similarly, F will be sheaves in, so coherent sheaves of support of dimension at most 1 on Y.
And hold on. Less or equal than 1, Q, or less or equal than 0?
Less or equal than 1. So there can be sheaves supported on curves now in this torsion pair, in the torsion category.
Okay. But the one should be right orthogonal, whatever, to the other one. Okay.
Yes.
Okay. So your category is coh less or equal than 1.
Yes. So let's see an example, or actually a non-example first. So let's see, this is Y, this is F, this is X. And let's say that we just contract one curve, which is a P1. Oh, maybe I'll do this by E. Okay. Let's say we have a smooth curve C that intersects E. Then this complex OY surjects onto OC union E. This is both a DT and a PT pair on Y, but it is not a BS pair on Y. The reason being that the structure sheaf of C union E lies in a short exact sequence. Yes. And OE minus 1, this sheaf is in the torsion part of the torsion pair, because its push forward to X is 0. But OC and OE minus 1 have an extension the other way. So there is F non-trivial extension. And then using this natural surjection to OC, we get the section, and this complex OY goes to F will be a BS pair. Because now the co-kernel of S is OE minus 1, which is torsion for this Bryan-Steinberg definition. Yeah. Okay, so as I was saying, Bryan-Steinberg introduced this wishing to give a geometric interpretation of that ratio that appears in the Krappan resolution conjecture. So they define this invariance. Well, they define some BS invariants using the spaces, using the Variance function. So, okay, and then they define some generating series, all denote them like this. And they also showed the following wall crossing, that the generating series of this invariance is the ratio dt y q divided by dt y exceptional q is the same as pt y q pt y exceptional q. The second equality follows from this Pandharipande-Thomas conjecture, which is known for Calabial threefolds. So we would like to define this invariant for Y not necessarily Calabial. Or maybe I should say here explicit for Y Calabial. And state similar wall crossing in the non-Calabial case. So as I was saying, in the non-Calabial case, we do not have this Variance function, so we actually have to construct this virtual fundamental classes. So there are proper algebraic spaces, yes, F and Y beta, parametrizing BS pairs with natural virtual fundamental classes that recover the Bryan-Steinberg definition when Y is Calabi-Yau. The expected dimension is the same as before, is the intersection between beta and C1Y. Okay, so this. So this allows us to define a generating series with insertions once again. And then the conjecture, similar to the Pandharipande-Thomas conjecture, is that BSF is this ratio of PT Y Q gamma K divided by PT Y exceptional Q in the following cases when y are insertions pulled back from x. For simplicity, I'll assume that they are curves or points on x. So in this case, the insertions will not yeah, it will be enough here to not put insertions in this exceptional PT series. So this is a conjecture similar to the PT conjecture. And we would like to prove it in some cases which are not Calabial, so cases which are not done in the PT conjecture. And one reason for believing that we can do something like this in this particular case is that if we use the generation formulas, this term of PT invariants on exceptional curves is sort of local, is near the positive dimension fibers, and maybe we can isolate it in one component with nice properties that we can analyze using some other methods. Whereas in the PT dt correspondence, the ratio was the dt theory of a point, which is all over X. So using a degeneration technique, you'll still get contributions of those on both sides in the degeneration formula.
And rationality question.
So this equality is a formal power series in Q.
Okay.
Yeah, so maybe I'll write here. So the theorem here is that we managed to prove this conjecture for a case when y is not Calabial. So the conjecture is true in the following case. For f, contraction of a curve, P1, with normal bundle in y o minus 1 plus o minus 1. So still y looks Calabial near C. But y is not necessarily Calabial. Okay, so in the remaining time, I'll explain the steps of the proof.
Yeah, okay, maybe one question. How much of that, actually, it's curious, can be generalized to quasi-projective when you do not have compactness of, because sometimes, you know, physicists, they are not afraid of anything, and they speak about Donaldson-Thomas and even Gromov-Witten theory for non-compact threefolds. And so I'm just curious.
Yeah, so usually in the subject, this approach is using virtual fundamental class work only when the spaces, the moduli spaces, are proper. So you can have X or Y not proper, but then you should parameterize sheaves with compact support.
Yeah, and sometimes, I don't know about Gromov-Witten, but for Donaldson-Thomas, when you have a torus section, probably you can define the equivariant count. And similarly,
That's correct. That's correct. That's correct. Yes,
okay.
yes, yes. That's right. Yes.
Thank you.
But I think the definition in the Calabial trick is using Variance function is more amenable to.
Yes. I think that the definition which uses torus localization is ugly. You should, it should be theorem, not definition.
Yeah. So in there, what is this? Yeah, in the remaining time, I'll explain the steps of the proof. So as I was saying, the idea is to use the degeneration formula. So initially, this is y, this is x. So we contract a curve onto a point. So we should be using this family. So we use deformation to the normal cone on C and Y. So the precise family is this. So over a non-zero complex number, the family looks like what I drew on the left-hand side, this contraction of C. Over 0, both y and x will have two components. So one will be, for y will be the compactification of the normal cone. This is C. This is sort of a picture of the normal cone. And here I add S. So maybe all this will be P, which is by definition the projectivization of O minus 1 plus 2 plus O. And then this S is the divisor at infinity, so is the it's O minus 1 plus 2. And the other component is the blow-up. Okay, so let's see what are the two components. So once again, there are two components. One is this P, which is a toric component that intersects the blow-up of Y along C along a smooth divisor S. And X will also have two components. Corresponding to the normal cone, it will have this component. So this is, I'll denote this by P prime. So this is, and this map by G. So P prime is the contraction of C in P. And here at infinity we have S, and this will be the blow up of X along P. So these two components on the right hand side are isomorphic. But on the left hand side they are not. So we still have a contraction of C. Now I'll mention the degeneration formulas. So for PT invariants is this one. So here I take P relative to S, Q, beta 1, beta, times PT blow up CY to N, factor of eta. And we have a similar formula for BS invariants. So here I have G relative to S, B1, eta, Q. Oh, so as I was saying, the map between the blow up for Y and for X is an isomorphism. And for identity maps, these Bryan-Steinberg pairs are the same as PT pairs. So the second factor is the same as the one above. Okay, so let's see. So what are these classes? So and also what are these relative spaces? So if you have such a degeneration of smooth xt into x0 and x0 prime, then the degeneration formula relates invariance on xt to relative invariance for x0 relative to s and x0 prime relative to s. So for PT theory, this was known by work of Li and Wu, and we prove it for Bryan-Steinberg in Bryan-Steinberg theory. And okay, so what are these relative pairs? So I'll discuss them for BS invariants. So this is P beta N. So they will be sheaves. There'll be complexes where the sheaf F intersects S transversely. So this will give an open locus inside BS. And for degenerations where S would not intersect, where F would not intersect S transversely, we add some bubbles. Okay, so these are P projectivizations over S of the normal bundle of S in the toric part plus O. Okay, so then by intersecting this F with S, we get elements, we get a zero-dimensional sheaf on S. So we get some element in the Hilbert scheme of points on S, where K is this intersection, so between beta and S. And now these classes are certain, maybe I'll just write it, certain cohomology classes on Hilb SK. So some Nakajima basis for Hilbert schemes of points on a surface. So one important feature here is that the insertion classes all go in the same part. And the reason is that the insertions were on X only. This was an insertion. So the insertions will be also when we use the degeneration formula just on this blow-up spaces, will not intersect the toric part. So this allows us to, okay, so maybe one more thing about these cohomology classes. So I should also say what are the terms that appear in this generating series. So for example, in this relative BS pair with no insertions, its terms, so this will be a sum after n. So it will be an integral after this, the virtual fundamental classes of these relative spaces. And here we don't have insertions anymore, but these virtual fundamental classes are not necessarily zero. So this P is not Calabial, but we will integrate some cohomology classes from the Hilbert scheme via this map epsilon. Okay, so kind of the first step in the proof is use the degeneration formula, and then we will need to compare this relative PT invariant for P, which is some toric threefold relative to S, a divisor at infinity, and the similar invariance for BS pairs. So then the second step is use localization theorem. So this spaces, the virtual fundamental classes of, as I was saying, of relative BS and PT pairs that appear here might be of dimension not zero, but let's use localization theorem. So what will happen is that, so we use localization theorem for a two-dimensional torus. So this is the torus that preserves the natural Calabial form on P minus S. So this was the total space of O minus 1 plus 2 on C. So what will happen now is that the restriction of a BS or PT pair on P minus the curve C will be an ideal sheaf of a T fixed curve, and those curves will have some fixed partition profile like this.
So, Tudor, I'm a bit confused. You mentioned that your moduli space is not a scheme, it's something like algebraic space. Either localization theory, maybe I'm just ignorant. For algebraic spaces, either just the same localization theorem where you divide by Euler. Yeah.
Yes.
Okay.
Yes, it's exactly the same. Yes.
Okay.
Yes. So this two-dimensional spaces, two-dimensional partitions. You know, you can think of that this BS or PT spares, they're on this fixed P1. So these are the fixed P1s, T fixed P1s on the toric space P. And they will be ideal sheaves. And so they will have, let's say, a parameter Z, a coordinate Z that it's free. And a picture like this tells you the thickening in the other X and Y directions. So we'll call, so there will be 4 such legs, and we'll have 4 partitions along these 4 legs. We'll call this pi. And let's write our class beta. So this will be, this is a class in H2. So this will be some class depending on the length, so the points here for a partition, times the homology class of legs plus some coefficient times C. So this is our C. And then we consider the spaces of T fixed sheaves denoted like this, BS and pi M, and PT and pi M. So now, using the localization formula, what we have is that the terms that we obtain will be something like epsilon upper star eta divided by the Euler class of virtual normal bundle integrated over BS and pi M, and for PT is similar. But this intersection, so the cycles eta will be near S, and also this so this normal bundles will be the same near S, because the spaces of BS and PT pairs are the same near S. They only differ on C. So actually, what happens is that it is enough to compare, so the integrand will be the same. So it is enough to compare the virtual fundamental classes themselves. And now these localized classes will have expected dimension 0. They behave like Calabial classes. So the reason is that this x1 and x2 for legs for this fixed P1s, so the T fixed P1s would be trivial. So, and on C, we can use Serre duality because the canonical divisor of P is supported on S. So let's see, this is the 3. So these classes have expected dimension 0. And now we can use this motivic algebra techniques. They have x1 is dual to x2 to deduce to finish the conjecture. So maybe I'll just write what we get. So for fixed P, we denote by BS pi Q. So there are no insertions now. And so this will be the series for BS invariants of fixed profile pi. And this will be the generating series for PT invariants. So now we show that BS pi Q equals PT pi Q divided by PT0. So this is where I don't have anything on this leg. So when my sheaf is just supported on the exceptional locus. So this proof follows closely this Bryan-Steinberg argument. Okay, yeah, that's all.
Thank you very much. questions, please? So then basically you do not avoid the wall crossing in the sense that you simply at the level of key fixed sheaves. Yeah, something.
Yes, I would say that the wall crossing is still the main tool in this proof. It's just that for this particular two enumerative theories, one can reduce a non-Calabi-Yau situation to a Calabial situation. Whereas in the main conjecture that one studies, this is not possible, or not obviously.
And by the way, this PT story from the very beginning, it's non-refined, it's enumerative invariants. And I understand that Bryan-Steinberg, it's two. What about the refinement? Since you use motivic whole algebra, so then yeah, so whether it's possible to actually it's rather a question all the way back to Pandharipande-Thomas, but what's the status of the refined invariants?
So refined invariants will be some elements in a motivic Grothendieck group, or will be more like cohomological DT, so cohomology of vanishing cycle?
It depends on your taste. Since you use a motivic whole algebra, so probably it's kind of better to use this motivic integration type, kind of K0 type motifs rather than cohomological. But I will be happy with any of these.
It's interesting. It's interesting. I'll think about it.
Yeah, cohomological, I think it's even more difficult beyond Calabial. Yeah, but still, I mean, your argument, I don't know. Your argument seems to be quite general. Whatever if you would be asked to compute the cohomology, you will also compute. It's first you look for the fixed locus, and then try to somehow.
Oh, but I guess so this in the non-Calabi-Yau case, I don't think there are refined invariants, but it's the question is very interesting.
In general, no. For fourfolds, Calabial fourfolds, probably yes, there is a replacement. At least in cohomological, there is a cohomological whole algebra. Probably, I don't know. Dominique tried to work out the details, but I didn't I don't know what's the status. Okay, okay, great. More questions?
I have a question, probably not quite relevant to your talk here. So in the earlier you used defining the E dimension, you use x1, x2 dimension. x1 is the deformation, and x2 between the ideal sheaves. Actually, it's called the obstruction. What happens if you take instead of the ideal sheaf, take the structure sheaf of the Z? What are these called?
Yeah, in that case, the reason is that one has a non-trivial x naught, right? This can be large. It's not zero dimensional.
I mean, from algebraic geometry view, what are those representing? I know it's going to be very hard to compute all those things. Yeah, you probably know it.
I know what.
So he was defining the E dimension using the x1 of the F, which is the ideal sheaf.
Yeah, but he wants the perfect abstraction theory, which for non-Calabi-Yau, it's problematic.
So what are the higher x's representing? Are they called the higher abstraction theory, or?
But I don't think there is higher than x3. Am I mistaken or what?
For threefolds, no.
No, for general higher dimension.
Oh, no. I mean, there are, even if you go back to this Pandharipande-Thomas story, they succeeded exactly because they have this perfect abstraction theory. And so, and as a result, they have this nice moduli space and invariant function and blah, blah, blah. So at least you can say the words. If you just shoot in the nowhere, your X is just a manifold, I mean, whatever, smooth, projective, even manifold of any dimension.
Yeah, that's it.
No, I don't know. It's difficult.
Yeah, I also don't know. I mean, also, I'm not sure this X3 or X4 in for general X, what they have to do with obstructions, but they appear as cohomologies for this cotangent complex. So that might not be supported in degree 0 and 1 for M.
Yeah, but you know,
kind of, it's a measurement of singularities in some sense. But
yes. But also you can try to work with higher DG stacks. I mean, you can pay much higher price in trying to develop the theory for and higher, but still you need some sort of a shifted symplectic structure in the end. No, whatever, after localization or before localization. Yeah, so I don't know. And just to define an enumerative invariant, first of all, it will not be invariant. For example, Donaldson invariants in four dimensions. So when the virtual dimension is not 0, you have to integrate some characteristic class, some differential form of whatever virtual or non-virtual fundamental class. And so the answer will depend on, for Donaldson invariants, the answer depends on the metric. Yeah, so it depends on that. So in the space of metric, there is a wall. People study wall crossing formulas, but in this ugly space of metrics, so it's certainly, it's not an entirely algebra geometric, at least by it's kind of from the beginning. Then you can try to consider complex surfaces, blah, blah, blah. But
yeah, actually, I'm more interested in see what the Tudor wrote on the screen. That instead of the ideal shift, taking the structure shift, but the X is taking on in the category of coherent shifts on X, on the modules.
Yes.
So that this and if I'm not taking the X, they taking the Tor for all the different Tors, and this is where the intersection theory. For the X,
quite understand what do you want in this case. So
you also assume that you have a torus acting on X, and you also take.
Well, before take the X, if I look at the resolution in the Tor, which is a very nice, as Jan mentioned, you have a very nice DT commutative DT algebra structure, but the X seems to be quite. So that I was curious what's in algebraic geometry all these X's are representing. Algebraically, this is always for some algebra, complete intersection is good, but for more general, the Z is very singular. The X's can be very large.
Yeah, you have sort of a category, whatever, in any dimension. Koch with dimension of support smaller or equal. Then you have some higher stack of objects. So I even scared to so it's a complicated thing, yeah. So it's kind of even this relation of which Tudor mentioned, Gromov-Witten invariants, which exist in any dimension under some conditions on the target, and Gromov and Donaldson-Thomas, it's in dimension 3. Yes, but you consider not you consider kind of sheaves supported on curves. Yeah, it's a dimension of the support is not very big, because in Gromov-Witten theory, it's you know, you consider maps of curves, and basically, roughly speaking, here you replace the modular space of maps to the modular space of their images. Yeah. Yeah, but there are some other DT. It's what physicists would say that this PT or DT story, rather DT, it's a theory of D0, D2, D6 brains. Well, yeah, for them, 6 it's three-dimensional. In physics, it's Calabial. 2 is a curve and 0 is a point. Yeah, but there are also D4 brains, surfaces. And if you include surfaces, the theory becomes more complicated, much more complicated. But here, these surfaces as supports of sheaves, they did not appear in the statement of the problem. It's just dimension, remember, dimension less or equal than 1 complex of the support. Okay, anyway, more questions? Okay, if not, then Tudor, thank you very much. May I ask you to send me the notes of your notes, and we'll post them together with the video.
Yes.
Of your talk.
Yes.